Good afternoon, everyone. Today is lecture number 23 of this heat treatment class, and today's topic are importance of austenite grain size and transformation or decomposition of austenite. So, we have started a topic in the previous lecture that is about this austenite only, where we have discussed the formation of austenite. So, suppose in that case we have taken an example where we have chosen an eutectoid steel which is having perlite, you understand, and you are hitting the steel above the eutectoid temperature, and we are getting austenite phase. That means this perlite get transformed into austenite. And if you remember, this grain size of the austenite is called the grain size of the steel also, if it is not specified. Basically, if it is specified, then grain size of the steel is different, but if it is not specified, then grain size of the steel is nothing but the grain size of the austenite phase only, and that is also called primary austenite. It is okay. And also we have seen, if we go to a higher temperature above the eutectoid temperature for an eutectoid steel, the austenite grain size will be bigger. That is basically due to diffusion, because diffusion is dominating at high temperature. And the thing is what also we have discussed about how the austenite forms. Basically, austenite also forms with same nucleation of austenite will be there, then growth of austenite will be there, right? And also we have seen the nucleation site for the austenite. Basically, austenite nucleates at the interface of the ferrite and cementite, right? And also we have seen that basically what are the factors that will affect the formation of austenite. Basically, those factors which affect the rate of nucleation and rate of growth. And also we have seen that the rate of nucleation of austenite is affected by the interfacial area. That means more is the interfacial area, more is the rate of nucleation of the austenite. And the interfacial area can be increased by increasing the carbon weight percent. Why? Because with increasing the carbon weight percent, we are increasing the cementite percentage. So more is the cementite, more is the interfacial area. So that's why it increases the rate of nucleation of the austenite phase. Right? And second thing, we have seen how the growth rate is affected. The growth rate is affected on the basis of the interlamellar spacing between the perlites. That is, interlamellar spacing in perlite means it is the distance between two adjacent center of the cementite, basically, right? So finer is the spacing, less is the distance for the diffusion of the carbon to the low carbon concentration area. So if the distance between the two interlamellar spacing, or distance between the interlamellar spacing will be minimum, or it is finer, then we have higher growth rate, right? Because the diffusion distance is decreasing. The carbon can easily diffuse from a high concentration region to low concentration region to form austenite phase, right? So these are the two things we have discussed in the earlier class. So today's topic is just opposite, that is the importance of austenite grain size and transformation. So in this topic, we'll discuss about the decomposition of austenite. So in the earlier class, we have discussed about the austenite formation, but here we'll discuss about the austenite decomposition and how it is decomposed, and what are the different products also. So before that, we'll discuss about the importance of austenite grain size. So first one is the relationship between grain size and yield strength. So this topic has been already covered in Introduction to Physical Metallurgy, as well as it has been covered in the earlier part of the lecture. So we people remember the Hall-Page relationship, or the Hall-Page equation, that is sigma y is equal to sigma naught plus k d to the power minus half. It's a very important expression. You have to remember that. This expression relates basically the yield strength of the material with the average grain diameter. Right? So it is basically saying that the yield strength of the steel increases with decreasing in the average grain diameter. So grain diameter decreases, the yield strength increases. Fine. So yield strength will increase. Right? This is from the Hall-Fetch relationship. But you have to remember, this is not always true for the grain size which are very fine, like in the nanometer scale. Right? If you go to a nanometer scales means it is a very fine grain. In that condition, this Hall-Page relationship do not work. Right? If the grain size will be more finer in the nanometer range, then the strength will not increase. But if it is in the micrometer, it is fine. They need both strength and ductility in the steel or metals. So suppose we need both strength as well as ductility, which are both opposite nature, then the best one is the grain size refinement or the grain refinement. So by reducing the size of the grain, we can increase both ductility and the strength. Or in other words, we are increasing the toughness of the steel or the material. Then motivation to the development of high strength low alloy steel. So we have particular kind of steel called HSLA that denotes high strength low alloy. So it clearly saying that the concentration of alloying element will be minimum, very low, right? So can anybody think of this? If we have a minimum alloying content or the alloying element weight percentage will be very minimum or very low, what advantage will get in the steel? Which kind of property is important here? The concentration of alloying element will be very low or the weight percentage of alloying element will be low. What advantage will get?
Ductility. Ductility.
Ductility. I'm asking in terms of okay, fine, ductility. But just look at this one. What is this? HS, high strength. So if strength will be high, how ductility will be more?
Uh, Toughness. Toughness value is more.
Toughness, that is fine. Any physical property will get affected? What is the major limitations of steel compared to that of aluminium? If somebody will
Strength to
ask,
weight, strength to weight ratio.
strength to weight ratio. Don't tell me strength to weight ratio. Just you can say weight or you can say density or specific gravity. That's all. The aluminium have very low density or low specific gravity, right? How much it is? What is the specific gravity of aluminium? It is 2.3, right? 2.3 gram per centimeter cube. It is very minimum. But still it is higher. How much? What is the density of iron? What is the specific gravity of iron? Hmm?
Sir, 7.87 gram per meter cube.
Yes, 7.8 nearly. 7.8, yes. The steel is how much? Sorry, aluminum is how much? 2. 2.7 gram per centimeter cube. So it varies actually, it depends upon the temperature also. So 2.7, so you can understand it's very minimum as compared to that of, that means steel is having high weight. The weight of the steel is very high for a same dimension of an aluminium. So high strength, low alloy. The alloying content will be very minimum, but strength is very high, right? So what advantage will get? Can you tell me right now?
Lightweight.
Yes, we can minimize the weight, or we can minimize the density, in other words. Right? So weight will be decreased if, because more alloying element will be there, then that means the weight will increase. If weight will increase, what problem will face basically? What kind of problem will face? If it will be used for automotive applications. If your application area is automotive one, what problem will face if the weight will be high?
More fuel consumption.
Obviously the consumption of fuel will be more, right? The consumption of fuel will be more. That's why there is a concept of development of nowadays supercars or car bodies with the help of these aluminum alloys. 7075 series aluminum alloys are used for car bodies nowadays. Entire car is made up of aluminum nowadays. All Audi's cars, all aluminum Audi cars, AA series. That is all aluminum Audi cars. The entire structure is made up of aluminum. There is no stress of steel because that aluminum alloy can provide very high strength, but it is very lightweight. We can save a lot of fuel, or we can say the fuel economy will increase, right? Anyway, so high strength low alloy steels, you understand that means the weight will be minimum, but strength will be very high, right? So these high strength low alloy steels are actually containing this very low amount of carbon, that is on maximum up to 0.02 or 0.25, not 0.02, 0.25. The minimum amount of carbon. Manganese concentration will be 28%, but other alloying elements which provide very high strength are vanadium, niobium, titanium. So these are the major alloying elements: vanadium, niobium, titanium. Right? So the motivation to development of the high strength steel is to minimize the density, basically, or minimize the specific gravity, or you can, in other words, you can say to minimize the weight of the steel, but to provide high strength. How high strength is obtaining? By addition of these alloying elements in a very minimum amount: vanadium, niobium, titanium. So can you people tell me how, if addition of these alloying elements will be there, how it increases the strength? How it increases the strength? How vanadium, niobium, titanium increases the strength?
So by forming alloy carbides.
Very good. By forming alloy. They are very strong carbides or weak carbides?
Strong.
Very strong carbides. How you can say they are strong carbides?
So because their dissolution needs very
High
large
temperature.
time
Yes.
and high time.
First one is high temperature. Yes. They require very high temperature, like above 1050. Is okay? So above 1050, still okay, fine. Suppose you have a austenite phase at 910 degrees centigrade, and these alloy carbides are there. So what benefit you will get? Okay, let me ask other people. Apurva Das.
Yes, sir.
Yes. Suppose you have a steel and your steel containing this niobium, vanadium, and titanium. And you are taking the steel to the 910, 12 degrees centigrade, right? Suppose austenite will start forming here. So what benefit you will get here due to presence of this niobium, vanadium, and titanium? Already Panda have told something that it forms stable carbides. So what advantage you will get? Tell me quickly. I'm waiting. Hmm? Okay, Ipsita Sahu, can you answer this one? Or shall I repeat the question? Ipsita Sahu,
Yes, sir.
can you answer this one? You have a steel which contains vanadium, niobium, and titanium, and you are taking the steel to 912 degrees centigrade. Huh? That means austenite formation is taking place. So, what advantage you will get at that temperature if you have these alloying elements? Panda, I have already told you that they form stable carbides, or basically
Yes, sir.
also they form stable nitrates also. Huh? Carbides and nitrites. He missed this one. So, what advantage you will get at that temperature? Okay, fine. Nikhil Singh Dev, can you answer this one? Nikhil,
Yes, sir. Yes, sir.
can you answer this one?
No, sir.
You understand my question? Nikhil, can you tell me what question I have asked?
Yes, sir. At 912 degrees temperature,
Mm-hmm.
what austenite will form? You have asked.
Austenite will form, but what question is? What is the question? Yeah, Swapnamai Panda, can you answer this one? Swapnamai,
Yes, sir.
can you answer this one?
No, sir.
Okay. Sonalata, Sonalata,
Yes, sir.
can you answer this one?
No, sir.
Raj, Raj,
Yes, sir. Yes, sir. I'm
can
here.
you answer this question?
Sorry, sir.
Yeah, Jivajoti. Yeah, Jivajoti can answer. Yes. Jivajoti, can you answer this one?
Yes, sir.
Can you answer the question?
Sir, during quenching, these carbides will these carbides will get formed along the grain boundaries, and they will grow. And
during
and
quenching, during quenching, how it will form? During quenching, everything will be in the solution.
Sorry, sir. So, like when you're taking the steel to high
Now,
temperature.
my question is: the steel is supposed at a temperature of 1000 degrees centigrade now,
Yes,
and you
sir.
have these alloying elements: vanadium, niobium, and titanium. So, what advantage you will get?
So they will basically provide high strength.
They will provide high strength. What is the need of?
Sir, they will
Yes.
get soluble throughout the matrix and give high strength after quenching.
So they will homogenize throughout the crystal.
Oh God,
Sir,
what you people are
grain
saying?
questioning, sir, grain
Panda
questioning will
already
not
have
suffer.
told these carbides and nitrates of niobium, vanadium, titanium are stable. They are strong carbide and nitrate former,
Sir,
and he
So
also
they will
said
Sir,
form
that they
a
will
sir,
not
fine
become
grains.
soluble.
sir, they
Yes.
will form bigger spheroid particles at that
Oh
temperature.
no.
Sir,
Sir,
we'll
grain
get
questioning will
ductility,
not
sir.
Carbides
suffer.
and nitrites will
Grain,
homogenize throughout the crystal.
No, Abhibhushan, wrong. Yes,
sir,
Panda, Soumya, can you answer?
sir,
Yes.
grain questioning will not occur because
Very good, very good. Excellent, Soumya. No, this is very simple. These carbides are still, these nitrates are still there. They are not becoming soluble. they will become soluble if you take to a very high temperature. So that means they are still stable at this 912 degrees centigrade or 1000 degrees centigrade. So they are stable means they are not becoming soluble. So they are still, they will be present around the grain boundaries of the austenite, right? So they prevent the coarsening of this austenite grain. They will not allow the austenite grain to become coarser. You people now understood? Or shall I repeat? You people have better understanding, or shall I repeat the answer of this one?
A little bit elaborate.
I'm talking about right now high strength low alloy steel. You people have understood what is the significance of high strength low alloy, right? Because alloying addition is very minimum, but we are getting a very high strength, right? The weight is very minimum, but we are getting very high strength. How this is possible? By addition of certain alloying elements like niobium, vanadium, and titanium. Sometimes we are adding some molybdenum, sometimes we can add some nickel, and some other alloying elements can be added for different purpose. But the major alloying element is the niobium, vanadium, and titanium. These are the major alloying elements. They are added in a very small amount, some 0.1, 0.2% like that. It is enough. So what is the advantage of this? The advantage of this is, even if you are austenitizing the sample at a very high temperature, these precipitates, these niobium, vanadium, titanium carbides or nitrides are still stable at high temperature. They will not become soluble at high temperature. If they are still at high temperature where austenite is there, so they prevent the growth of austenite grain. They do not allow the austenite grain to become coarser. So if we have a finer austenite grain at austenitizing temperature, and we are doing suppose quenching, or we are doing some any other transformation, what advantage we'll get? We'll get a finer grain structure after transformation is over. It is okay now? It is okay, or again I will ask the question. Just tell me if it is well, or I will explain again. The final grain structure depend upon the austenite grain structure. If austenite grain structure is bigger, the final product obtained will be also of bigger grain size. It is okay, or shall I ask the question again? Okay, Ipsita Mishra, can you answer this one? What is the significance of this vanadium, niobium, titanium in the steel at high temperature? Suppose,
Sir, the audio isn't too clear, but can you repeat the question?
what is the significance of vanadium, niobium, titanium alloying additions to a steel at high temperature, like suppose at 1000 degrees centigrade? What advantage will get at 1000 degrees centigrade due to presence of these alloying elements? Yes.
It's for rust, resisting the formation of rust.
It prevents the, yeah, what you're saying? It resists the?
To resist the formation of rust.
Formation of what?
Rust.
Rust. Do you
Sir,
think this?
RUST, rust, to prevent oxidation.
Okay, fine. Do you know? Yeah, you have the class of corrosion. I think you already have taken the subject corrosion, right?
Yes, sir.
Which elements provide resistance to corrosion?
Resistance to corrosion, like chromium.
Yes, chromium. So have I talked about any chromium right now?
No, sir. You talked about vanadium.
Yeah, vanadium, niobium. So they are they providing any resistance to corrosion? You are saying?
Okay,
let
they
me.
can
Okay,
carbide.
Yeah. What carbide?
I'm
Okay,
not.
Latmika, can you answer it briefly? I want, because I know you can answer it. Yeah.
Yes, sir. So it's prevent grain coarsening
Which
and
grain
gives
portion? Which kind of
precipitation
grain?
stability.
Just elaborate the answer. Like at 1000 degrees centigrade, what phase will be there, and what will happen if these carbides or nitrates will be there? Yes.
Sir, at 1000 degrees Celsius, the phase will be austenite.
Very good.
And
Yes.
austenite, due to presence of these vanadium, niobium alloying elements,
Mm-hmm.
the grain coarsening will not occur at
Yes.
1000 degrees Celsius.
Very good. So if grain coarsening will be not occur, what will be the advantages after transformation?
So after transformation, fine grains will get.
With there, yes. Very good. Very good. Okay, fine. I think you people have understood right now. If you have any questions, you can ask me right here. Yeah, Aditya Acharya, can you answer this one? Aditya?
Yes, sir.
Can you answer this one? Okay, Aditya, gold is a ductile or gold is very ductile or it is a brittle material?
Ductile.
My question is, it is very ductile or brittle?
Very ductile.
Ductile, only ductile. Okay. Okay, Amiz Khan, gold is very ductile or brittle?
Sir, gold is ductile.
Ductile, okay. Amrita, gold is very ductile or brittle? Pure gold?
Sir, very ductile.
Yes, very ductile. Very good. So why you people are saying it is ductile? It is very ductile. If you can press the gold by your hand, if you have a very pure gold, it is so ductile.
Yes, sir, pure gold is very ductile.
Why it is very ductile? Can you justify in terms of physical metallurgy? Let me see how many of you can answer. Why gold is very ductile? The question is common to everyone. In terms of physical metallurgy, how gold is very ductile? Structure, property, correlation. Yes, tell me. Already I have justified this one. Okay, Pritishika, can you answer this one? Why gold is very ductile? Pure gold is very ductile. Why?
Very ductile. Why? Sir, because if we beat into its wire, then
Don't tell me those
don't
answers.
tell me
My
those
question is
answers. My question is
why gold is very
why
ductile?
gold is very ductile.
I am not asking the
I am not
property of
asking the property of the
what is ductility.
what is ductility and all.
Sir, it is FCC.
Yes, very good. Who have answered?
Who have answered?
Who have answered this one?
Sir, Chandan.
Chandan, yes, Chandan, very good. Yeah, it is the crystal structure of gold is FCC, and we people know the if the metal have FCC crystal structure, it have lot of active slip systems, and if we have a lot of active slip systems, that means we have lot of what chances of having slip, or there is a easy chances of slip happening, and slip is a mechanism of plastic deformation. That means the metal will easily deform plastically on application of a very minimum shear stress. Or critical resolve shear stress will be very less for FCC metals. How many slip system we have in FCC?
Sir, 12.
Very good, 12. What is the slip system and slip direction in FCC? What is the slip plane and slip direction? Because slip system means it is a combination of slip planes and slip directions, right? How many of you remember?
Plane in 110 direction.
110 direction, 110 plane. Very good, very good. If you have a cube, can you tell me the plane from where to where it is? 111. I'll give you a cube and I want to ask you to draw a 1-on-1 plane. Okay, this is an assignment, huh? I think you people should brush up your mind, huh? At least you people have forgotten everything. This is an assignment. So the assignment is draw draw 2 cubes, right? Draw 2 cubes and draw a hexagon and show. And first cube is your FCC, second cube is BCC, and third cube is not cube. That third is HCP, or that is basically hexagonal structure. Show me different planes, huh? 1-1 plane, 1-1-0 plane, and 1-1-1 direction and 1-1-1 direction, and your 0-0-0-1 plane. So this is your assignment, huh? Okay, I think you people have understood the concept of HSLA, high strength low alloy. So the motivation behind this one is we have to add very low alloying element, or the weight percentage of alloying element will be so low that these alloying elements have a tendency to form strong carbides and nitrides, basically. And they are very stable at high temperature, like up to 1050 degrees centigrade. So even we have an austenite phase at 1050, but the austenite grain will be of smaller grain size, because these carbides or nitrides are forming along the grain boundaries. They prevent the coarsening of the grain. They are acting as a pinning agent. They're pinning the grain boundaries. They do not allow the austenite grain to grow bigger and bigger at such a high temperature, 1000 degree or 1050 degrees centigrade, right? So that means, in other way, I can say they provide strengthening by precipitation and along the grain boundaries, and they prevent the grain coarsening. So in other words, I can say also they keep the grain smaller in size, or that is grain boundary strengthening. If we have a smaller grain, so there is more obstacle to the dislocation motion. It is okay. So this is the concept. So you understand the relationship between the austenite grain size and the strength and high strength low alloy. Then grain size versus impact transition temperature. This is also a good concept. You people understand impact means sudden loading, sudden force acting on the materials. So basically, when we'll have a sudden loading or sudden impact force acting on the material may fracture easily, right? So it should withstand the sudden impact loading, right? So basically, it has been seen that if we have a finer grain, then that is good actually. Finer grain have high toughness, so fracture resistance will be more, or resistance to the fracture will be more. So material may break by ductile mode, not brittle mode. But if we have a coarser grain, if the grain size is more, the impact transition temperature is actually increases. You're right. So impact transition temperature increases with increasing in the grain size. So that means bigger grain size will break easily by brittle nature. In other way, I can say. So bigger grain structure will break easily by brittle mode, basically when we are reducing the temperature, because there is a ductile to brittle transition temperature is there, right? If you go to a low temperature, there will be a ductile to brittle transition will happen, right? So that means at a very low that means relatively low temperature will be there, but the material will break by brittle nature if we have a coarser grain structure. Because of this one, because of impact transition temperature will increase. But if we have, that means for finer grain, impact transition temperature will be very low. The material may break by ductile mode, not by brittle mode. Then relationship between creep strength and grain size. So basically, you people remember, creep is a failure mechanism. The material fails. It is also, we can call, plastic deformation is happening at a high temperature, right? So resistance to creep how resistance to creep is affected by grain size. This is the question. So to make it understand, we'll discuss some points. That is, what is equicohesive temperature? Do you have any idea about equicohesive temperature? What is equicohesive temperature? You people have heard about this term elsewhere in DBM or in phase transformation? Have you ever heard about this one? Equicohesive temperature? No. Okay, fine. Do you people have any idea about the strength of grain boundary and strength of the grain interior?
Sir, at high temperature, the grain boundary becomes weak, due to
Very
which
good. Very good.
it
Very good.
slides.
Yes, yes. So you people have studied about creep mechanism, I think.
Yes, sir.
In which subject?
DBM.
DBM. Yes, very good. That's why that's why I have asked this question. Equicohesive temperature. Equi means equal. Cohesion means there is a cohesion, addition, cohesion, like that, and there is a temperature. So equicohesive temperature is that temperature where the strength of grain boundary is equal to strength of grain interior. It is okay now? Shall I repeat? Shall I repeat or it is okay? So equicohesive temperature is that temperature where the strength of the grain boundary is equal to the strength of the grain interior, or the strength of the grain is equal to strength of the grain boundary. Right? So that means you can understand the strength of the grain interior and grain boundary is not same. It depends upon, it is a function of temperature. If we go to a very high temperature, the interior grain and the strength of the grain boundary will be different. Similarly, if we go to a low temperature or near to the room temperature, the strength of the grain interior and the grain boundary will be different. So the thing is what? That means we can have a situation where our temperature is higher than equicohesive temperature, or we can have a situation where our temperature is below equicohesive temperature, right? So below equicohesive temperature, basically grain boundary is stronger, or it has high strength as compared to grain interior. But if we go to a high temperature, or the temperature is above equicohesive temperature, the grain boundary will be weaker, or the strength of grain boundary will be reduced.
Hello?
Yes, Amrita. Yes, Amrita, you can speak. Yeah, if you have any questions, you can ask me. Okay, so you people have understood this one. What that means? What happens to the strength above and below equicohesive temperature? The answer is grain boundary strength reduces above So for every material, we have an equicohesive temperature. So if you go above the equicohesive temperature, the grain boundary become weaker. In other words, the strength of the grain boundary become reduced. Fine. And you people understood, if the grain boundary strength will be reduced, and grain boundaries are, you understand, is the boundary between two grains, right? What will happen then? The grain will slide against each other. There will be sliding of the grains, or there will be grain will move past each other easily if we apply a shear stress. It is okay now? So which one of the mechanism works at high temperature which leads to creep failure? So one of the mechanism is what I can write, due to which the creep will be happening. Tell me quickly, what is that mechanism? Due to creep will have happen. What is that? What is that?
Grain boundary sliding.
Grain boundary sliding. So grain boundary sliding means the grain boundary become weaker at above the equicohesive temperature, right? So once it become weaker, they will slide past each other, or they will just move past each other. So material will deform. The material will deform means at the end it will fail by creep mechanism. So this is one of the mechanism. It is not for every mechanism, because creep failure occurs by other mechanisms like diffusion of vacancies, dislocation climb, grain boundary migration. You might have heard about these terms. Anyways, so what is the conclusion? Can you people tell me now? What is the conclusion? Okay, sorry. What is the conclusion between the size of the grain and creep strength? I think this part we have discussed in the strengthening mechanism. In which case coarser grain is required, in which case finer grain is required. What is the situation where coarser grain are advantageous and where finer grain are advantageous?
Sir, if you need a ductile material, coarser grain are not required.
Don't tell me those kind of thing. My question was based on creep. And
Sir,
my
at
question
very high
was,
temperature, we
yes,
require less grain boundary. That's why coarser
very,
grains are required.
very good, very good, very good. So basically, you understand many things are important here, right? So basically, coarser grain provide high creep resistance. Finer grain provides low creep resistance. It is okay? Because creep is the dominating mechanism there at high temperature. And finer grain will be leads to more diffusion, because more is the grain boundaries, more is the easy path for diffusion. That is one part. And another part is, as I told, the grain boundary will get slide, or grain boundary sliding will happen. If we have a coarser grain and we have a finer grain boundary sliding will be easier in which case? Who can answer?
Finer grain.
Yes, finer grain will be sliding more. It is okay right now? So what I can write? The relationship between the grain size and the creep strength or creep resistance to creep?
More grain size, more creep resistance.
Yes, very good. If we have a coarser grain material, it provides resistance to the creep, basically. Because finer grain material have some problems. One is the diffusion one, and one is the grain boundary sliding. Right? And grain boundary sliding is related to the equicohesive temperature. And diffusion mechanism is related to the number of grain boundaries. More is the grain boundaries, more is the easy diffusion path. Okay. So now the question is creep resistance of cast steel versus forged steel. So can you people tell me now? You have a cast steel. Cast steel means just after casting. Just after solidification. Then forged steel means you are doing forging. Suppose you are doing hot forging after doing casting. So can you people tell me quickly? Let me see who can answer this one.
Sir, creep resistance is more in forged steel.
Creep resistance is more in forged steel. Can you justify that?
In forging, we are taking our steel to very high temperature. At that temperature, grain coarsening occurs. That's why we acquire less grain boundaries. So creep
Okay.
resistance is more.
Okay. Anybody want to try? Yeah, Pranav have tried somewhat, but can you people try this one? Okay, fine. You people have forgotten. If you do hot forging, what will the grain size? What will happen to the grain size if you do hot forging? Suppose you have taken the steel to 1000 degrees centigrade and you are doing forging. Everybody know forging? Yes or no? Okay, Alok Kumar Jai Singh, can you answer what is hot forging means? Alok Kumar Jai Singh. Alok Kumar. Alok Kumar Jai Singh. Okay, Alok Kumar Jai Singh is absent. Ankit Aniket Baral.
Yes, sir.
What is the meaning of hot forging?
Sorry, sir, I don't know.
You don't know. Okay, fine. What can you tell me? What is forging?
So it is a type of working.
It is type of
Yes.
which
Metal working.
metal working.
Hot working. Yes.
It is type of hot working. Working here means what exactly we are doing? That is the question. My question. Which kind of force is which kind of force you are applying on the material?
Tensile.
Tensile force. Okay. Okay. Raj. Sanjeev. Okay, Sanjeev Kumar. What kind of force we are applying during forging? Sanjeev Kumar. Sanjeev Kumar. Swarnalata Samal. Swarnalata. Swarnalata. Veer Sangram.
Yes, sir.
Yeah, Swarnalata, what kind of force is acting on a material when you do forging? Yeah, Apurva Das, what kind of force we apply on a material when we do forging?
Sir, compressive force.
Yes, who is saying? Swarnalata, compressive force. Can you justify how it is compressive?
Sir, by hammering and offsetting, we are applying force.
No. My question is, hammering is a forging, I understand. But can you justify how it is a compressive force? You are saying compressive force. Somebody have told me it is a tensile. So how you can justify that? Okay, Rameshwari Patra. What kind of force is acting on a material when you do forging?
Sir, compressive force.
Yeah, can you justify how it is compressive?
No, sir, Jordan.
You should tell me the direction of force, no? That will justify. What's the direction of force on the material?
Direction inward होगा सर टेंसाइल फोर्स में तो बाहर को ना कंप्रेसिव फोर्स में भीतर को होगा डायरेक्शन में फोर्स
Okay, fine. Anyways, Adarsh Naik, what is the direction of the force in forging?
Sir, outwards?
Outward direction.
No, then maybe inwards. I'm sorry.
It is compressive force is acting on the material or tensile force is acting on the material when we do forging?
The tensile force.
Tensile force. Okay. Have you seen the tensile test in the previous lectures?
Yes, sir.
In the tensile test, what happened to the tensile specimen?
It breaks. No, it does not break, but it extends.
Okay, it extends. So in the tensile test, what kind of force is acting on the material?
Tensile force.
Tensile force leads to what? Then extension of the specimen. Okay, very good. So you are doing hammering on a material. Huh.
In the case of hammering, it uses compressive force.
Yes. Now it is fine. Compressive force. Can you tell me the direction of the force?
Inwards.
Inwards. You are doing hammering. How it is inward? Can you justify?
If we attack the breadth of a rectangular object, then it compresses. So the length will decrease.
You people don't know simple things. Inwards, obviously inward force, because some force will come from the bottom, from the ground to upward, and you are striking with the hammer. So you are applying an inward force from the top, and from the bottom, from the ground, a force will come. So obviously it is a compressive force.
Yes, sir.
Okay, now can you pick who can answer? In the hot forging, you are forging the steel at 1,000 degrees centigrade. So what is the grain size? How the grain size will be affected? What kind of mechanism will? Okay, yeah, Lathmika, can you answer? I think you can answer. The steel is at 1,000 degrees centigrade, and you are forging the steel at such a high temperature. Forging means you are deforming the steel plastically, right?
Yes, sir.
Yeah. So what will happen to the grain size?
Sir, coaster.
Sir,
Temperature is 1,000 degree.
Sir, elongated grain size.
Elongated grain size you will obtain upon plastic deformation, right? But the temperature is high. Temperature is also there. Now that means you have a condition right now. You have a deformed grain, the grain with lot of strain, lot of defects, dislocations, but temperature is high. What will happen?
Recrystallization.
Yes, fine. You will have recrystallization, but that means you will have recovery, then recrystallization, right? But if you keep for a more interval of time at high temperature, then grain growth may happen at the end. So what will happen now? If you will not keep at a very high temperature or for long interval of time, so what will the grain size?
Finer strain-free grain.
Finer grain. Why finer grain? Because of recovery and recrystallization, right? It is okay? It is okay or not? Suppose you insert a steel into the furnace at 1,000 degrees centigrade. After certain hour, you take out it and you hot forge it. So what will happen? If temperature will be available, then obviously you will get finer grain also. It will get elongated first, then due to strain, lot of dislocations, new grain will form. So you'll get a finer grain basically after forging, hot forging, right? But what about cast steel? After casting, what is the grain size? Bigger or smaller?
Bigger.
Very good. Why bigger? Can you justify?
Because of slow cooling, sir.
Yeah, and because of slow cooling.
Sir, no work has done upon the specimen.
No work is done. That is fine. The thing is what? You will get dendrites. Dendrites are smaller grain or bigger grain?
Bigger grain, sir.
Bigger grain because they grow in a particular direction. They are big size, right? Dendrites are tree-like structure. Do you remember right now dendrites?
Yes, sir.
It is like columnar structure. Columnar structure are actually simple grains, but they are elongated grains. But dendrites are tree-like structure. They have many arms: primary arm, secondary arm, tertiary arms, right? And they are single big crystals. If the crystals are big and in a particular direction, that is not good actually. So dendrites are never good. never helpful for our properties because they are bigger in size and they have a directionality. They grow in a particular direction from mold wall towards the center of the mold. Okay, fine. Now, can you people tell me? So, cast structure have coarser grain. Forged steel have finer grain. So, creep resistance will be higher for which one? Tell me quickly.
Cast.
Creep resistance. Very good for cast. So nowadays we are casting this single grain materials for our high temperature applications. Like for turbine blades, we are casting single grain materials nowadays. Single grain, you understand? It will be a very big grain. Yes or no? Single grain, but it is a very big grain. You people understood now? Okay, last question. Silicon deoxidized steel versus aluminum deoxidized steels. Okay, you have a subject steel making, right?
Yes, sir.
Okay, how many of you remember? Yeah, I have taught you extractive metallurgy, right? Or who have taught you this unit process of extraction?
So you.
Yeah. So how many of you remember what is deoxidation practice in steel? Deoxidation practice. Okay, how many of you remember how steels form from iron? From an impure iron, how steels form?
By reduction, sir. In the blast furnace.
By reduction. My question is how steel forms from impure iron. I'm not asking about iron. Okay, how iron forms from ore? What is the mechanism?
Reduction.
Ore, it's reduction.
Yes, that is either you can carbothermic reduction. Okay, anyways, reduction. Or in what is the other name? Reduction is fine, but any other name it has? If you are getting pig iron, what is the other name? Smelting. Smelting. Okay, anyways. So upon reduction, we are getting iron. But how steel is obtained?
Oxidation.
By oxidation. Very good. Oxidation of what?
Impure iron.
Oxidation of?
Impurities.
Impurities. Very good. Oxidation of impurities. You can go through the UPE notes at least again to the chemical method of refining. At least you go through the notes. Oxidation. You will oxidize the steel. So upon oxidize the steel, what will happen? The impurities will get oxidized, but the iron will not get oxidized. So impurities will oxidize means it will become oxides. And once it become oxide, it will move to the slag phase. Anyways, that is not our topic, but our concern is after blowing oxygen into the impure iron, we are getting a steel, right? So after getting a steel, this contain lot of oxygen, dissolved oxygen. We have to remove that. So that removal of dissolved oxygen from the steel is called deoxidation practice. That can be done by addition of alloying elements or some elements. Like can add silicon, we can add aluminium. But can you people tell me, silicon deoxidized steel versus aluminum deoxidized steel, which one have high strength? Which one have high strength? Just think of it. If you add aluminium into the steel containing oxygen, what kind of product will form? What kind of product will form? The moment you add aluminium into the steel containing dissolved oxygen, what will form? According to Ellingham diagram, what will form? Aluminium oxide, yes or no?
Yes, sir.
That is the purpose of deoxidation. Aluminium will go and react with oxygen to form aluminium oxide. Aluminium oxide is a solid. It will come out of the steel. So this is the way by which we can decrease the amount of oxygen in the steel, or we can decrease the dissolved oxygen in the steel. Similarly, you add silicon. So what will form? What will form if you add silicon into the steel containing dissolved oxygen? Silicon oxide, obviously, SiO2. Because they are forming there, because they are more stable oxides. Okay, fine. So can you people tell me, that means you will end up with steel containing SiO2 and end up with steel containing Al2O3. That means in a very minimum amount, negligible amount. Most of the oxides will remove. But suppose you end up with a steel containing Al2O3 and you'll end up with a steel containing SiO2. So which one will have finer grain structure? Which steel will have high creep resistance, in other words? So that will depend upon the grain size. We still have high grain size and we still have low grain size. The steel containing aluminum oxide have low grain size. Why? In the previous class already I told you, if you want to reduce the grain size, then you have to add some alloying elements, vanadium, niobium, aluminum, because they form either carbides, nitrates, or oxides, and they remain in the grain boundaries. So they pin the grain boundaries. So that means aluminum dioxide steels are finer grain steel, but silicon dioxide steels are not finer. Is okay? So what will happen? So silicon dioxide steels have high creep resistance. Okay, I will end the lecture here. We'll continue our lecture from the next class.